Dear students, after studying this module, you shall be able to know about the significance of atomic absorption spectroscopy, the basic principle and methodology, and types of application of atomic absorption spectroscopy. Atomic absorption is a process involving the absorption of light by free atoms of an element at the wavelength specific to that element. It means by which the concentration of metal can be measured in their atomic state. In various phenomena of atomic spectroscopy, which could be emission, absorption and fluorescence, energy is supplied to the atoms in the form of thermal, electromagnetic, chemical or electrical energy, which is converted to light energy by various atomic and electronic processes before measurement. Atomic absorption spectroscopy is useful not only for the identification but also for the quantitative determination of many elements present in the samples. The technique is specific and sensitive in that individual element in which in each sample can be dependably identified in a small amount. This technique was introduced by analytical purpose by Walsh and Alkimade under the designation atomic absorption spectroscopy. Walsh used the hollow cathode lamps as the light source, greatly reducing the resolution required for the successful analysis. As photomultipliers had become accessible, the complications associated with measuring the absorption with photographic plate were eliminated. His introduction of modulation into the system permitted the detector to distinguish between absorption and emission by atoms at the same wavelength. He also utilized the flame for atomization. It is found to be superior to the other techniques as it can be used to determine 50 to 60 elements from trace to large quantities. These may include metals and non-metals. Principle of atomic absorption spectroscopy. The principle is based on the Beer-Lambert law. The absorption of radiation by the free atoms is proportional to their concentration. It is given by the relation absorbance is equal to log 10 to the power of I0 by IT, which is equal to KCl, or log 10 I0 by IT is directly proportional to the concentration. Here I0 is the intensity of the incident radiation, IT is the intensity of the transmitted radiation, C the concentration, L the path length and K as a constant. Methodology. The sample solution is aspirated into a flame or heated in a tube to convert them into atoms by the process known as atomization. The atoms then absorb the radiations of the characteristic wavelength, promoting the electrons from the ground state energy level to the excited state. Each element absorbs radiation of a particular wavelength, which forms the basis for the qualitative analysis. Depending on the number of atoms in the light path, the amount of light absorbed also changes. By detecting this amount of light, a quantitative determination of the analyte can be made. Each atom contains a positively charged nucleus surrounded by number of electrons in a rapid motion around the nucleus. For each electron in each atom, there is a discrete set of energy levels that the electrons can occupy. The spacing of the energy levels is different for each electron in the atom, but for similar atoms, corresponding electrons have identical spacing. The energy levels are usually labeled as E0 for the ground state and E1, E2, etc. to infinity. For an unexcited atom, each electron is in the ground state. To excite the atom, one or more electrons can be raised to the first or higher energy levels by the absorption of energy. This energy can be supplied by photons or by collision due to the heat. Those electrons furthest from the nucleus require least energy to go from the ground state E0 to the first energy level E1. The energy E corresponds to the energy gap between the ground state and the first energy level, that is E is equal to E1 minus E0. The energy required for the transition can be supplied by a photon of light with an energy given by E is equal to h mu, where h is the Planck's constant and mu the frequency of the radiation. This corresponds to the wavelength lambda, where lambda is equal to h into c by E, where c is the speed of light in vacuum. Instrumentation of atomic absorption spectrophotometer. An atomic absorption spectrophotometer apparatus consists of, firstly, the radiation source. The common source of light is a hollow cathode lamp HCl. This contains a tungsten anode and a cylindrical hollow cathode made of an element to be determined. These are sealed in the glass tube filled with an inert gas, that is neon or argon, at the pressure of about 1 Newton per meter square to 5 newtons per meter square. The ionization of some gas atoms occur by applying the potential difference of about 300 to 400 volts between the anode and the cathode. These gaseous ions bombard the cathode and eject the metal atom from the cathode in the process called as sputtering. Some sputtered atoms are in excited states and emit radiations characteristic of the metal as they fall back to the ground state. These emitted radiations form incident radiations for the element under analysis. Atomizer. Nebulization is the mechanism by which the sample solution is introduced as fine spray into the flame. Nebulization refers to the dispersion of a liquid into particles by rapidly moving gas, liquid stream or mechanical means. This process is immediately followed by atomization, wherein high energy like that of a flame converts molecules into atoms. Flame atomization. The burner and the nebulizer helps in the atomization of the element. Atomization occurs in the flame and an atomic vapor of the element to be analyzed is produced. The selection of the flame temperature is important for atomization. When it is low, atomization will be partial, and when it is high, the atoms may get ionized. Graphite furnace atomization. A graphite furnace can be employed instead of the flame for atomization. The atomizer may be elongated along its axis to increase the distance between the optical path and the sample deposition point, which increases the analytical sensitivity. Oxidants and fuels. Fuels commonly used are hydrogen, propane, butane, acetylene and natural gas. Oxygen and nitrous oxide are used as oxidants. The oxygen acetylene flame is most often used. Its temperature is high enough to cause sufficient atomization for most elements, which can be determined by AAS, but not so high that the ionization interference becomes significant. The analytical conditions can be optimized by changing the composition of the gas mixture. The temperature limits for some of the gas mixtures is tabulated here in the given table. Monochromator. It is important that the instrument be capable of providing a narrow band width to separate the line chosen for determination from the other undesirable lines. Usually used devices are gratings or prisms. Detectors. Photomultipliers are commonly used as detectors. In some instruments, additional filters and detectors are used to compensate for the fluctuations in the output of the source. Output of the photomultiplier is amplified, which helps in the source modification. Functioning of the atomic absorption spectrophotometer. Atomic absorption spectroscopy uses the absorption of light to measure the concentration of the gaseous atoms. Since samples are usually liquid or solids, the analyte atoms or ions must be vaporized in a flame or graphite furnace. The atom absorb ultraviolet or visible light and make transition to the higher electronic energy levels. The analyte concentration is determined from the amount of absorption. In this process, a blank solution is sprayed into the flame and the meter is adjusted to zero absorbance or 100% transmittance. Following this, the solution under the investigation is sprayed. The atoms in the ground state absorb certain part of light, resulting decrease in transmitted light or increase in the absorbed light falling on the photomultiplier tube. The readings can be tabulated, and with the help of the standard graph, the concentration of a particular element in the sample can be found. Applications of atomic absorption spectrophotometry. Atomic absorption spectrometry has many uses in the different areas of chemistry. The different methods of atomic absorption spectrometry are very powerful for analysis elements in a solution. The instruments are simple and easy to operate. They are useful when few elements have to be determined in large number of samples, as is the case of clinical and food analysis. Atomic absorption spectroscopy methods are of great importance compared with the other methods of elemental analysis. In clinical analysis, it is used for analyzing metals in the biological fluids such as blood and urine. In environmental analysis, it is utilized for monitoring the levels of various elements in the rivers, sea water, drinking water and air, etc. AAS can trace presence of pesticide residues in fruits and vegetables. In pharmaceutical industries, it is used for the assay of drugs. Purity of the sample can be checked for the minute quantities of the catalyst used in the manufacturing process, usually a metal, sometimes present in the final product. Levels of the toxic substances present in the products can be verified and reduced by this technique. By using atomic absorption spectrometry in mining industries, the amount of metals such as gold in rocks can be determined to see whether is it worth mining the rocks to extract the gold. Sensitivity and detection limits of AAS. More than 70 elements can be measured by atomic absorption spectroscopy. The lowest concentration that can be quantified in the sample depends upon many factors. In spectrometry, the sensitivity for an element is defined as being the concentration expressed in micrograms per liter, which in an aqueous solution leads to 1% decrease, that is absorbance of 0.0044 in the transmitted light intensity. So for manganese, this value is 4 pg with the aqueous matrix. When possible, a calibration curve should be established with the concentration in the range of 20 to 200 times this value. In practice, the concentrations must be at least 10 times higher than the detection limit to give the reliable measurements. To summarize, this technique was introduced for analytical purpose by Walsh and Alchemid under the designation atomic absorption spectroscopy. It is found to be superior to the other techniques as it can be used to determine elements from trace to the larger quantities. Atomic absorption spectroscopy AAS is an analytical measurement method relying on the spectroscopic process of excitation. It is used for the qualitative and the quantitative analysis of around 70 elements, metals or non-metals. In atomic absorption spectroscopy, the absorption of resonant radiation by the ground state atoms of the analyte is used as analytical signal. This process is highly selective as well as very sensitive. The functioning of atomic absorption spectroscopy is based upon the principle of Lambert-Beer's law. The sample is first converted into an atomic vapor and then absorption by these atomic vapor is measured at selected wavelength characteristic of atom of each element. The amount of light absorbed is proportional to the concentration of the element. In its simplest form, an AAS resembles a single beam spectrophotometer which contains four principal components: the light beam issuing from the source passing through the burner, in which the element is brought to its atomic state before being focused on the entrance slit of the monochromator, which selects a very narrow wavelength interval. The optical path ends at the entrance slit of the detector.